Next on our schedule is Chapter 3, in which we're just going to do the first section, which is on systems of equations. We might briefly touch on the second section, which is basically the same idea extended to three variables. But I wanted to review the process of solving multiple different equations at the same time, and this recognizing certain specific situations. So there's three main ways that we could solve a system of equations, and we'll look at each of them very briefly. But before we get into how, I wanted to talk about what are we looking for and what is the main idea. So in a system of equations, we typically will have more than one equation, obviously by the meaning of system, and what we're looking for is a solution that works in both of them at the same time. So it's sort of like an and situation. We want to make sure that it's working in this one and in this one. And not or. We don't want it to work in either or. Though that technically could be something you care about. It would just be a different meaning, of course. And one of the things about a system of equations is they always involve more than one variable, because if it was two different equations with only one variable, they might have different answers, and it might not be possible to solve both of them. But based on each equation individually, it's helpful to think about, well, what does each equation look like, and why would there be a solution to both of them? But like looking at this example, it asks us, is 6 comma negative 1 a solution? What about negative 3, 5? And we could always just plug the values in to see if it will work, and that's kind of how we can understand whether a value will be the solution to the system as a whole. And it must be a solution to both equations to be a valid solution to the system. If it only works in one or the other, or in neither, it's not a solution at all, of course. So if we were to plug in 6 comma 1, we would have, well, 2 times 6 plus 3 times negative 1 is equal to 9. And that would, not sure why that is showing. Hopefully that goes away. That would be 12 minus 3, which is, of course, equal to 9. Oh, I think I have a weird setting on my tablet. Okay, that should fix it. And so notice that in this case, 12 minus 3 is 9. Cool. But, that's one part of the puzzle. What about the other? Does 6 comma negative 1 work in the other? So if I were to plug it into the second equation, I would have, well, negative 5 times 6 minus 3 times negative 1. And that's supposed to equal 0. That, of course, does it. That would be negative 30 plus 3 equals 0. Definitely not true. So basically, no, 6 comma minus 1 is not a solution to the system. What about negative 3 comma 5? Well, again, we could just plug it in. That would give us 2 times minus 3 plus 3 times 5 equal to 9. That would be negative 6 plus 15. That is definitely 9. So far, so good. Plugging it into the second, we would have negative 5 times negative 3 minus 3 times 5 equals 0. And that's definitely true, because that would be 15 minus 15, which is 0. So basically, we see that this one is a solution. And that's always the goal when we're solving a system, is to figure out a value that works in both. And now something you might be wondering is, there only one point that will work, or could there be multiple? Very rarely could there be multiple solutions. In a system that has more than two equations, it's actually less likely that it would have more than one, but it is possible in very, very specific cases, and we'll get into those, but generally you're only going to have one point solution. And this brings us back to the first method of solving a system of equations, which is by graphing, because each one of those equations, the graph of which would look like a straight line, since they're both x and y without any other shenanigans going on. And basically, if we could imagine each line with having a slope and an intercept, and whatever those lines look like, the lines cross, they will have an point of intersection, and that is the point of commonality, because each line represents the equation. It's a visual representation of the pattern within that equation that's relating x and y. And ultimately, those lines typically overlap. Now, unless the two lines are exactly parallel, meaning if they have exactly the same slope, then they will not intersect unless they're overlapping. And in the case that they're overlapping exactly the same line, then that's the only case that we could have more than one solution, or infinite solutions. But you could always, I wanted to show you how you could do this in your calculator. Now, to graph such equations in a calculator, we want to make sure that you need to solve it for y first, because if you turn on your calculator and go to y equals, or if you're using a TI-84 at least, it's expecting the equation to be solved for y, aka in function form. So if we went ahead and solved each for y, well, that would give me 3y is equal to negative 2x plus 9. And then if I divide by 3, that'd be y is equal to negative 2/3 x plus 3. And in the second equation, if I wanted to solve for y, I could add 3y to both sides and divide by 3, which would leave me with y is equal to negative 5/3 x. So we can see that the first equation has a slope of negative 2/3 and an intercept of 3. The second has a slope of negative 5/3. So those will not be parallel. So that means that there has to be just one solution, because if they're not exactly in the same direction, then they will overlap in just one point. Since again, they're straight, right? If they're straight, they're not going to have any curves, and they can't come back and connect more than once. Anyways, we have negative 2/3 x. I just wanted to show you how you can solve these with a calculator if you want, because this is, method number 1 for solving a system. And this takes no understanding of, the algebra, and it's a way you can always check the solution to your system, assuming you can get the calculator to work. So after this is done graphing, I'm going to change my calculator window back to a more standardized window. So if you hit zoom and then number 6 is zoom standard, it will set it to, a normal negative 10 to 10, negative 10 to 10 domain. And that way it'll be easier to see sometimes. Now, the point of intersection on the graph, let me go ahead and make this graph a little bit bigger. It may not be in a position where we can see it, because this is not the whole graph. This is just a finite window. So that's one of the weaknesses of this method, but you can always use the window feature to customize what you're showing. Basically customize, well, what is the domain and what is the range that the calculator is displaying. That way you can look in other places if you can tell, well, okay, the point of intersection is not going to be to the left or to the right or whatever, up, down. But basically, if you want to see where these points cross, we already know the solution is negative 3, 5 because we verified it. And if we're eyeballing it, we can see negative 1, 2, 3, negative 1, 2, 3, 4, 5. Oh yeah, this is negative 3 and this is 5. But it can be a little bit hard to tell exactly where they're crossing. And one thing you might not be sure about when you're looking at it is that right on the point or not? Because as we know, sometimes math is not pretty, sometimes it's messy, and we want to figure out where there's an overlap when it's not necessarily pretty. But basically, I wanted to show you that you can find a point of intersection by going into second trace, which is the calculate menu. And notice that number 5 is called intersect. Basically, you can find the point of intersection between two different curves. And what you want to do is notice when you do that, it will ask you for the first curve. And basically, you just want to, oops, I clicked something on accident. You just want to move the blinking cursor to as close as you can to the point where they cross. And then if you hit enter, it will ask the same thing for second curve. You hit enter again. And guess, hit enter again. Basically, it just wants you to zoom into the point, and how the calculator does is it hones in on the correct value using a very numerical method that no point getting into right now. But anyways, we can find the point of intersection, which is, of course, again, the same thing as the solution to the equation. So if you're wondering, well, how could I come up with such an answer? That's one method, and we're going to be reviewing the algebra behind other methods, both the substitution and elimination method, in the next couple videos.